I'm going to review the homework on linearization that you have done in your packet, and in this particular year it's packet page 11. So let's jump into the problems. One of the key things you want to pay attention to is how I decode and how I unlock the problems. So the first problem says, what is the linearization? So the first thing you have to know is, what do they want me to do when I'm doing the linearization? And you can see that the root word of linearization is a line. So what we're looking for here is the equation of a line, and that line is a tangent line, and my line is tangent to the graph of e to the x, and the point of tangency, or the x value of tangency, is at x equal to 1. So obviously when you are told to write the equation of a line, you're going to write the point slope form of that equation, which says you're going to need a y value, you need an x value, and you need a slope. This is a tangent line. They gave us the x value of 1, and we can substitute that x value of 1 into the original function to get the y value. So e to the first power is e, so that's how I got the y value. And to find the slope of the tangent line, I'm going to find the derivative of the original function f. The derivative of f of x, or the derivative of e to the x, is e to the x. I'm substituting my x value of 1 into the slope generator, and e to the first power is e, so the slope of my tangent line is e. So I have everything that I need. I'm going to substitute into y1. I had a y value of e. Into the slope, I also had a slope of e, and my given x value was 1. And this is a multiple choice question, and I can see that in each of these it says L of x, but L of x is simply a y value, and I can see that they have y by itself. So the first thing I'm going to do is I'm going to add e to the right hand side, and they don't leave it in point slope form, so I know that I'm going to have to distribute e times x is ex. E times -1 is negative e, and then I added the e to the right hand side. These two e's subtract out, and I get y equal to ex is the equation of the line tangent to e to the x at x equal to 1, and that is letter B as in baby. Problem number 2. In this problem, we start with a function that has a derivative. F is a differentiable function. Therefore, I know that f is continuous. They're giving me the x value of 3 and the y value of 2, and they're giving me a slope of the tangent line at 3 to be 5. So slope is 5. And you can see that I recorded the same thing in my work. There's my 0.32. There's my slope. If the tangent line to the graph of f at x equal to 3 is used, I can't really use it until I have the equation of the line. So I'm going to go back like I did in number 1. I'm going to write my point slope form of the equation. I'm going to substitute the x value of 3. I'm not sure why there's a 1 there, x minus, I think that's just supposed to be x number 1. So I'm going to substitute my x value of 3, substitute my y value of 2, and my given slope to be 5. I'm going to clean that up. I'm going to distribute the 5. That's where I get 5x minus 15. I'm going to add the 2 to both sides. And so when I clean up, the equation of my line in slope-intercept form is y equal 5x minus 3. Now, it says I'm supposed to use that tangent line to find an approximation. So they're telling me this is going to be an approximation to a 0. Some students get confused, but what do you mean to a 0? This simply means a 0 of the function, meaning the function, you can see right here, I'm going to set the function, or in this case the line, 5x minus 3. I'm going to set that equal to 0. That's what it means to find a 0. It's an x-intercept, as you can see right here. And so when I solve, I get x to be 13 over 5. And 13 over 5 is 2.6, which is letter C. Going on to problem number 3. In problem 3, and by the way, this is an actual AP problem, they give me a table of values, and I can see that I have time in minutes. I have the derivative, so this is r prime measured in feet per minute. So these are rates. Let's read the prompt. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r. So that means that there is a function, basically whose name is r of t. To be twice differentiable simply means that there is an r prime of t, and there's also a second derivative of t. That's what it means to be twice differentiable. Let's go back to the prompt. T is measured in minutes. For the interval from 0 to 12, the graph of r original, so r of t, is concave down. So I'm just going to kind of do that to remind myself that the graph is concave. The graph of the original, let me put an r here, is concave down. So in terms of thinking linearization, if the graph of r is concave down, then that tells me that my tangent lines, whatever is going on here, are going to be above the curve, and approximations will be too large. The table above gives selected values of the rate, the first derivative, r prime of t, of the radius of the balloon from 0 to 12. The radius of the balloon is 30 feet when t equal to 5. So when t equal 5, r, the length of the radius, is 30 feet. One of the most important things to do is to be able to decode and take apart all of the clues of the problem. The volume of the sphere is given by this function right here, v equal 4/3 pi r cubed. In this problem, I'm not even sure that the volume equation is going to come into play. As I said, this is a real live AP problem, and I pulled one part out of probably 3 or 4 parts of a problem. In this problem, I am estimating the length of the radius of the balloon when t equal to 5.4. So there's that key word we're going to estimate using a tangent line. Use the tangent line approximation at t equal to 5. So I need to write the equation of the tangent line, and we want to decide if our estimate is greater than or less than, but we kind of already have the answer back up here. We know that since r is concave down, the tangent lines will be above the curve and the approximations will be too large. So I'm going to take the information that they gave me. As I indicated earlier, they told me that t is equal to 5, r is equal to 30. So I'm going to substitute that in as my x value, substitute 30 in as my y value, and then from my table of values, I can see that r prime of 5 is the slope of the tangent line, which is 2. That came directly out of the table of values, which goes here. I'm cleaning up my equation, getting y by itself, and in this case I am getting my equation into slope-intercept form. So this is the equation of the tangent line. I'm going to use that equation to make an approximation, so I'm going to substitute 5.4 in place of x. When I do the arithmetic, I get 30.8 feet. And the question was, is this estimate greater than or less than the actual y value? Well, my sentence says the estimate using the tangent line is greater than the actual true value of r, because r is concave down, meaning that the tangent line would be above the curve, and therefore the y values produced on the tangent line would be too large. All right, 2 more. Problem number 4. This is another real live AP problem. In this problem, we have solutions to a differential, meaning I'm going to give you an equation that has a derivative. That's what a differential equation is. It's an equation with a derivative. You can see that right here. This is an equation. dy dx is a derivative. So I have the first derivative given right here. and I have the second derivative given right here. I didn't have to do any work to produce those. Let f of x be a particular solution. So f of x takes me back to the original function, meaning that there was a function f of x that produced this, that has this first derivative and this second derivative. They're also giving me an x value of 1 on the original function and a y value of 2. So those are all of my clues. I had to process what I have, what I've been given. Letter A, here we go again. Write the equation of a tangent line. I already have the x value. I already have the y value. So I'm going to need to produce the slope. Well, good news. We have a slope generator right here. But this slope generator needs both the x and the y value. So I'll substitute 1 in place of x and 2 in place of y. So if you look at my work right here, I started out by writing my point slope form of the equation. I substituted the x value of 1, substituted the y value of 2. Over here, you can see that I substituted 1 and 2 in place of the first derivative. I got a slope of 8. That's the slope of my tangent line. So I substituted that here. I distributed, added 2 to both sides, and this is the equation of my tangent line. For part B, they want me to use my tangent line to approximate 1.1, so I'm going to substitute 1.1 in place of x and do the arithmetic. I get a approximated y value of 2.8. Last question, is the approximation greater or less? Hopefully we know that that's all about the concavity. And that's not bad because they give me the second derivative, which can tell you about concavity. So I'm going to grab my second derivative from above. I'm going to substitute the x and y value and carefully and slowly do the arithmetic. I get an output that is greater than 0. 104 is greater than 0. And since the second derivative is positive, the original function is concave up, the tangent line would be below the curve, and the approximations would be too small. So my statement says, since the second derivative is greater than 0 at 1, 2, original function f is concave up, so the tangent line is below the curve, and the approximation is less than the actual value of f at 1.1. And finally, number 5, another real live AP problem. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. So the first thing I notice is at 2010, which is time 0, there are 1,400 tons of solid waste. The increasing function that may come into play and be very important, W, models the total amount of solid waste. Planners estimate that W, the total amount of solid waste, will satisfy the differential equation, meaning that the original function is W and the first derivative is right here. This is my first derivative of the total amount of waste. This is the rate at which waste is increasing in this landfill for the next 20 years. W is measured in tons, T is measured in years from 2010. Here we go again. Use the tangent line to the graph of W at t equal to 0. We already have our x value and our y value, or our t value and our w value. It's kind of important to note that we have a t and a w, even though you can use an x and a y. I think you can get away with that. So I need the equation of the tangent line. So job number 1 is write the equation of the tangent line and then use the equation of the tangent line, job number 2, to approximate the amount of waste in the landfill for the first 3 months of 2010. So if time is measured in years, 3 months is a quarter of a year. 3 months out of 12 months is 1/4 of a year. So let's go down here and take a look at my work. So as I said, I recorded my time to be 0. The amount of waste is W. I need a slope for the equation of my line, so I substitute 0, 1400, and in this case it only needs the W value, so I'm substituting 1400 in place of W into the given slope generator, and I do the arithmetic and I get a slope of 44. So my output value is 1400, my input value is 0, and the slope of my tangent line is 44. Getting y by itself, this is the equation of the tangent line. And they said after you get the equation of that tangent line, use it to figure out how much waste is in the landfill in 3 months, a quarter of a year. Substitute, do the arithmetic, and I can see that there will be approximately 1,411 tons of waste. And no surprise that they're going to ask me next to figure out whether that approximation is too large or small, so I need concavity. So they give you a heads up. They're like, okay, first, find the second derivative. Now, students, pay very close attention. Implicit differentiation is coming into play here. So we know from above, they gave us the first derivative back up here. And you'll see in just a moment, to make my life easier, I'm going to distribute the 1/25th to make my differentiation easier, or I think it's easier. So when I distribute that and do a rewrite, I end up with 1/25th W, and 1/25th of 300 is 12. So now my work is easier. When I take the derivative of first term, I'm going to do it implicitly. So the derivative of 1/25th W is 1/25th, and then I'm going to take the derivative using the chain rule, dW dt. That's my chain, that's my implicit differentiation that I had to do to take care of the chain rule. That's my second derivative. So now I'm supposed to figure out at W equal to, what is W equal to? At what time are they figuring out? Let me go back and read the prompt. When in doubt, read. Oh, our answer so at T equal to 1/4 of a year, and we found out there would be 1,400. Okay, so here we go. So first, I'm going to substitute what dW dt is. We did this when we did implicit. When that dW dt is, you have to substitute what you know to be equal to dW dt. We know that dW dt is 1/25 times W minus 300. If you distribute that in, 25 times 25 is 1/625, still leaving the W minus 300 in parentheses. And if you substitute 1,411 in here, which I didn't actually explicitly show that, but I'm going to get a positive number. 1,411 minus 300 is positive, divided by 625 is positive. So the second derivative, when there's 1,411 tons of garbage, is positive. So the original function W is concave up, and the tangent line is below the curve. Therefore, the approximation is an underestimate of the amount of solid waste. Note, it is given that W is an increasing function and the amount of waste is initially 1,400 tons. I don't necessarily know why I said that, but it's in there. So hopefully this helps you with any problems that you ran into on this particular homework assignment.